molecular orbital theory. This is also known as linear combination of atomic orbital model. Now, before starting this molecular orbital theory, let me first tell you what is the difference between the atomic orbital and molecular orbital. The first point of difference is, in atomic orbital, the electron cloud extend around one nucleus. If this is one nucleus, the electron cloud will extend through one nucleus only. While in molecular orbital, the electron cloud will extend or range in between the at least two nuclei. The second point of difference is, atomic orbitals are of course less stable because the whole electron cloud is being influenced by the single nucleus, while the molecular orbital is expected to be more stable because this electron repulsions in the electron cloud are predominantly lowered by this influence or the attraction of this electron cloud or control of the electron cloud by the two nuclei. The next important point is, this atomic orbitals are having quite simple shape. As you know that s orbitals are spherically symmetric, p orbitals are d are double dumbbell, but the molecular orbitals are having quite complex shapes. The next very important thing what we would like to share, that is the difference between the valence bond theory and molecular orbital theory. The first point of difference is, in valence bond theory we actually consider that the valence electron would undergo the influence of the two nuclei and other electrons would retain their identity. While in molecular orbital theory, the valence electron as well as core electrons both are equally important for the formation of bond or participation in covalent bond formation. Now, let's explain this by taking an example, say suppose in two molecules. What we know that in nitrogen, we have the configuration 1s2, 2s2, 2p3. And if we consider this orbital diagram, it is having this 2p3, and as we have seen through the overlapping concept, this pz orbital is going a sigma bond, pz direct overlapping sigma bond, py pi bond sideways overlapping, and px also pi bond sideways overlapping. So here what we have seen, that it is the valence electrons which are only taking part in bonding. So valence bond theory only considers the participation of valence electrons. But when we will see the formation of dinitrogen through molecular orbital approach, we will see that the 1s electrons are also involved in bonding, the 2s electrons are also involved in bonding, and 2p, all the 3 electrons are also involved in bonding. That is, as per the molecular orbital theory, all 7 electrons in nitrogen are involved in bond formation, and thereby they finally decide what will be the bond order. While considering only the valence bond theory, we will see just the overlapping of direct or lateral, that is sideways or head-on overlapping, would decide the sigma and pi bond formation of nitrogen. But finally this two will converge into that point only, that nitrogen is having a bond order of 3, or nitrogen is having the strength of the triple bond. Okay, so the next one is, valence bond theory considers the particle nature of electron. Was what we know that usually electrons are having the dual nature like the light. So the particle nature as well as the wave nature, and we have also discussed that we have the lots of supporting evidences for the particle nature as well as wave nature. Valence bond theory considers the electron just as particle, while the molecular orbital theory extends the wave nature of electron, and thereby we actually consider the electrons as the orbital wave function or psi wave function, just like this waves. And the C waves, as we know that this is the amplitude or the maximum displacement of the wave. So what happens if two C waves are, just one is going and another is going on the same direction? This is called the in-phase overlapping or in-phase superposition of wave. In that case, we will get, if suppose this is psi A and this is our psi B in one direction only, so we will get finally a larger wave whose amplitude is actually the sum of this and this. So this is the combination of atomic orbitals what we will consider through molecular orbital theory. It could be in opposite direction also. One wave is in this direction, another wave is countering this. This will be the out phase direction. So we'll come to the next in the formation of linear combination of atomic orbitals.